I'm Rohit Kumar Singh, the TA for this course, Experimental Physics 2. This is the 8th live session, and uh, today I will recap some concepts from optics and some experimental methods like Newton's rings experiment and Michelson interferometer, and also I will solve some example problems from these topics. So let's start. Newton's ring. So, Mr. Sankar, do you know something about Newton's ring experiment? You can unmute and respond. It would be better to interact uh, rather than just me talking. Hello, can you hear me? Sankar Kuppan, can you hear me? If you can hear me, you can respond. Okay, maybe there's some. So, what is this Newton's ring? Now, it's a very simple experiment. So, suppose you have a glass plate like this, and you place a plano-convex lens like this on the top, and then you have a source of light here, and no, I mean you can have the source of light here, and then you can place a mirror here, and you can use a silvered glass. So suppose the light is coming like this, and it will get reflected in this direction and in this direction. So now some of the light will get reflected from here, some of the light will get reflected from here. Now these two light rays will have some path difference due to this thin film, due to this thin gap between the lens and the plate, and thus it will it will lead to interference, and you can observe uh, interference pattern if you look it at from above. So the interference rings will look like something like this. So radius. So these rings are called Newton's ring. Okay, so and there are many properties of these rings, and so I'll just write those properties. I'm not going to write the detailed derivation. Okay, so one thing that so this thickness between this lens and the glass plate is denoted by T. Okay, and yeah, and then this the radius of the ring. So this is suppose the center, and this radius of the ring. So mth ring will have the radius Rm. Okay, and it's given by uh, Rm square is equal to 2Tr, and this R is the radius of curvature of the lens. Okay, of this convex planar convex lens. And then we have the condition for bright ring and dark ring. So uh, since so suppose uh, this lens has refractive index mu, and so you can write the path difference as 2 mu t, and the condition for bright ring will be 2n minus 1 lambda by 2. Okay, so let's write it m. Okay, so this is the condition for bright ring. Okay, so I think we have some more people. uh, Hello, can any one of you respond if my voice is okay? Am I audible? Sankar, Sahida, Talat. Oh, okay. Can you speak? Okay, thank you. So, okay. So I was just talking about Newton's ring. So, do anyone of you know about Newton's ring uh, from before, or is it new to you? Okay, I'll assume that uh, you might have some knowledge of interference. And so yeah, I was just explaining how Newton's rings are formed. So basically you have to take a glass plate, uh, this glass plate you need, okay, and then you have to use a plano convex lens, this plano convex lens, and you shine a light on it, and because it has two surface, it has a two surface, one this convex lens, one light will be reflected from here and other one from the below plate, and since this both these lights are coherent and there will be a path difference between these two, so that introduces a phase difference, and so there will be interference, and you will get uh, interference pattern like a ring, uh, like concentric circles, okay, and these concentric circles are called Newton's ring, fine, and the radius of these circles is given by, so the mth circle radius is given by 2tr, where t is the uh, thickness of this gap between the uh, film and between the plate and the lens, okay, and then we have this condition for bright ring, uh, which is this 2 mu t is the path difference between the two light rays, and it should be equal to this condition 2m minus 1 lambda by 2 for uh, getting the bright ring, okay, and now what you can do is in the place of t you can put uh, from this formula rm square by 2r, okay, and then here same thing. So you can write the radius of the mth bright ring as 2n minus 1 lambda r by 2 mu, okay, so this is a very nice equation, or you can write it in terms of diameter, so dm square will be just so it will be 4 times, so this 2 will cancel in the denominator, and so you have 12 minus 1 lambda r by mu, okay, and for dark rings you just have 2 mu t is equal to m lambda, okay, condition for dark rings. So, and again you can put uh, at the place of t from this formula rm square by 2r, okay. Here you have 200, so you can write rm square equal to m lambda r equal by mu, and you can write the diameter as 4 times m lambda r by mu. Okay, so this is the radius of a bright ring, and this is the radius for a dark ring. And now what you can do is uh, you can use this Newton's ring to calculate the wavelength of the light that you are using. So how will you do that? So basically, uh, suppose you have nth dark ring. Okay, mth dark ring, you have the diameter as 4m lambda r. So suppose for now this medium is air. Okay, so mu is equal to 1. And so suppose the next dark ring, so suppose m plus pth dark ring will be at m plus p lambda r. Okay, now you can subtract these two equations, and you will get dmp square minus dm square by 4pr. So in this way you can calculate the wavelength of the light you are using from this Newton's ring experiment. So this formula will be very helpful for us. Okay, and so yeah, that is all we need for today from Newton's ring. Now I'll also discuss Michelson interferometer a little. So have you heard about Michelson interferometer? Any one of you? Hello, can you hear me? Do you know about Michelson interferometer? Okay, I'll assume that you don't know. So, oh, you know. Okay. So, what do you know about it? Can you tell me a little bit? Why do we do this experiment, the Michelson interferometer experiment? So it's a very important experiment historically. Uh, you might have heard about uh, Mike, Michelson-Morley experiment, in which they use this Michelson interferometer to conclude that uh, there is no ether medium in our universe, and which helped Einstein to uh, give his theory of relativity. So yeah, it's very interesting, and so let me draw schematics of this experiment. So suppose there is a source of light here, and you have a silvered glass like this, and this is a mirror. Okay, so suppose the light beam is coming like this. Uh, some of them will just pass, okay, and some of it will be so get reflected. So and you have a mirror also here. So this is M1, this is M2. So some of it will goes like this and then return back, and then from here also this will return back and go like this. Okay, and suppose here you are observing. Okay, so you will see that uh, this this light which is coming here, it will be seen to be coming from an apparent source M2 prime, because this glass has reflected the light in this direction. Correct, this, suppose this is the second beam, this is the first. Okay, so this second beam will be appear to be coming from behind this mirror M1. Okay, and given that these two path lengths, this, suppose this is x1 and this is x2. So suppose x2 is greater than x1, so then you will see two sources of light coming from uh, above. Okay, and hence you will observe an interference pattern. Okay, and here the condition for uh, destructive interference is given by 2d cos theta equal to m lambda. Now what is this cos theta? So this cos theta is simply, let me draw. So suppose this is two dimension, this is a mirror M1, and you are observing this. So the fringe pattern will be like these circles, and this is your theta. Okay, and so this is the condition for getting constructive interference. Oh, sorry, for destructive interference. That means a dark green. Now, uh, now this theta can be very small uh, in some cases, and so accordingly we can uh, the theta will vary from, so suppose 0 to some angle, okay, and accordingly you will get uh, rings at different location. Okay. So now one thing here one should notice is that, so suppose you change this distance d between these two mirrors, between m1 and m2. Now what will happen is that, since this changing the distance, uh, the theta will change, okay. So this the fringes that you are getting here, the rings will either collapse or either appear, okay. So suppose at the center you have cos 0, so you have this condition 2d is equal to m lambda at center, and now uh, if you increase the distance between these two mirrors, okay. So suppose you increase it by so suppose you move the mirror uh, m1 by distance d0, then you will have uh, 2d minus d0. So suppose, so doing that, n number of fringes will appear or collapse, okay, and hence from these two equation you will get this condition, okay. So this says that if you move the distance between the two mirrors by d naught, n number of fringes will n number of rings or fringes will appear or disappear, okay. So this is also a very interesting result, and I will use that in our problems. Yeah, so this is all we need. So do you have any question here? Should I proceed? Okay, I guess not. So let me go to our first problem today. So the first problem is based on Young's double slit experiment that we discussed in the last live session. So the question is, what will be the effect of fringe width formed in Young's double slit experiment if the apparatus is immersed in water? So this is a very simple problem. We know that the fringe width is given by this formula d lambda by t. Here, uh, suppose this is the two slits, and the distance between the slits is small d, and big D, capital D is the distance between the slits and the screen, right? And this is the theta. Suppose this is the point where the fringes are observed, and distance between the two consecutive bright or dark fringes is given by beta, which we calculated to be lambda d by d. Okay. Now, if we're changing the wavelength, sorry, if you're changing the medium, what will happen? So, you know that uh, for different medium, the wavelength of the light changes, right? So, and this is it changes by this formula. So now, if you're immersing it in water, uh, this mu for air is 1, but for water this mu is uh, greater than 1. So wavelength of light will be less than 1, sorry, less than that of the wavelength of light in the air. Okay, so that means now the fringe width will be less than what we have in the case when uh, we are using we are keeping the apparatus in the air, correct? So the correct option is it decreases. Is it okay? It's a very simple question. If you have something to ask, you can ask. Okay, if not, let me go to the next problem. So here we have uh, another question on interference. So the question is, what would be the resultant intensity at a point of constructive interference if there are two identical coherent waves of intensity I producing an interference pattern? Okay, so the intensity of uh, two waves is given. So intensity is I, and they are they are going uh, they are doing constructive interference, so we need to find the resultant intensity. Now for constructive interference, the phase difference should be so we can assume the phase difference should be 0, that is cos phi is cos 0, or it can be m pi in general, where m is the integer numbers. Okay, so uh, the value of cos phi is just 1. Okay, now the resultant intensity is given by I1 plus I2 plus 2 under root square I1 I2 cos phi, right? Is it okay? This formula you know, right? Because for amplitude we have this formula that the resultant amplitude square is just a square plus a2 square plus 2 a1 a2 cos phi, and amplitude square is proportional to intensity. Okay, so we can just put at the place of a square I resultant I1 I2 2, and for a1 you have to write under root I1, and a2 you have to write under root I2. Cos phi will remain the same. Okay, so you know the individual intensity is just I, so I plus I plus 2, so I square under root is just I, cos phi is 1, so we have 4I. So the intensity will be 4 times. So you see, for the constructive interference of two waves of intensity I, uh, the intensity doesn't get just doubled as amplitude does. It, it gets quadrupled, like become 4 times. Okay. Any question here? Shahida, Talat, is it okay? Are you able to hear me? Oh, okay. So, are you able to understand, or do you have any question? Okay, if you don't have any question, then let's move to the next problem. Here again we have a question on Young's double slit experiment. So this you have to answer, okay? So in Young's double slit experiment, if the distance between two slits is halved and distance between the slits and a screen sorry here. Okay, so let me read it again. In Young's double slit experiment, if the distance between two slits is halved and distance between the slits and the screen is doubled, then what will be the effect of on fringe width? So, what do you think will be the correct answer? It will remain unchanged, decreases by 2 times, increases by 2 times, or increases by 4 times. So, can you answer? What should be the correct option? Hello? You can answer in the chat box. You can calculate it, right? I've just written the formula for fringe width. So you should be able to answer it. Sahida Talat, do you know how to get the answer? If you don't know, you can just say no. I will solve it then. Can you please respond? You don't know? Okay, so just in the in the previous question, I wrote this formula for fringe width. Okay, so this here, see, this is the formula for fringe width. So same formula we have to use here. So the question is, if the distance between the two slits is half, that is d becomes d by 2, and the distance between the slit and the screen is doubled, that is capital D become 2. Okay, then what will happen on the fringe width? So let's put it here. Okay, so yeah, you are right, it will be 4 times, so lambda will be same, d is 2d now, and this is d by 2, so it will be 4 times lambda d by d. Okay, so it increases by 4 times. Mr. Sankar, There is noise coming from your side. Can you please mute yourself, or you have? Okay, thank you. If you want to speak, you can unmute and speak. Okay. Okay, so this was also an easy question. So now let's go to the fourth problem. Now here we have a diagram. Uh, so the question is, the following ray diagram is related with, so which of these experiments? Which SIP film, biprism experiment, Newton's ring, or Lloyd mirrors experiment? So which of these four options is correct? Do you know about this figure, this ray diagram? It's a very famous experiment. I just told you about it in the starting. I think you guys were not joined then, but you should know about this experiment. So, which of the option is correct? Anyone? Hello. You should know this. This is so. I just talked about this in starting of the lecture. So this is the same thing. Uh, you have a glass plate and you have a plano convex lens, and the interference pattern that you get here are concentric rings, and it's called Newton's ring. So same thing is here. So this is a Newton's ring diagram of a Newton's ring experiment. Okay, this is your plano convex lens. And this is the glass plate, and this is the thickness of the thin film, thin air film that you have between the glass plate and this lens. Okay, so let's go to the fifth problem. It is a problem on Michelson interferometer. So the question is, when a thin plate of refractive index 1.5 is placed in the path of one of the interfering beams of Michelson interferometer, a shift of 40 fringes is observed. Now, if the thickness of the plate is 0.02 mm, the wavelength of the light used is. So now, what 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 is given here is that, so we had this setup for Michelson interferometer. Right, this is our silver glass. We had a mirror here, and then we were observing the interference pattern here. Okay, and we were observing a apparent source of light M2 prime, and then we had interference between the light coming from M2 prime and M1. Okay, so now we are introducing thin plate. Okay, so that is, and its refractive index is 1.5. Okay, and the fringes shifted by, so the shift in the fringe P is 40. Okay, now, and this thickness of the plate is given 0.02 mm, and we have to find the wavelength of the light. So how do we do that? Any idea? So first, let's talk about the path difference introduced by this thin plate. Okay, delta x. So since its thickness is t and the refractive index is mu, the path length, the increased path length of the light will be 2 mu t, right? Because the light is going and coming back, that's why this 2 factor is there. And the increase in path length will be this subtracted by the actual path that is the light is traversing, which is 2t. Correct? So we can take 2t common. This is the path length difference between which is now introduced. Is it fine? Or do you have any question here? So, so now this is the path. We have calculated the path difference, and I told you uh, if you increase the uh, distance between the two mirrors, uh, you have this condition. Uh, sorry. Okay, so you have this condition. Let me try this. Yeah, I showed you this. If you change the distance by d naught, you have this condition that n number of fringes will appear or disappear. Correct? So we can use this formula, but here we are not changing the distance between the mirror. Instead, we are introducing a glass plate, and that will change the uh, path length of between the two interfering beams. Okay, So we can just use this as our D naught, and here we have P lambda. P is 40, right? So we can calculate the wavelength of light using this expression, -1 by P. So thickness is given 0.02 mm, and refractive index is 1.5 divided by P, which is 40. So we will calculate, and we will get the answer as 5000 angstrom. Okay. Any question? Hello? Okay. If it's okay, then let's go to the next problem. Here again, we have a question on Michelson interferometer. So here the question is, when the movable mirror of a Michelson interferometer is shifted through 0.022 mm, okay, that is D naught is given 0, and 100 fringes cross the field. The number of fringes which appears are given as 100. Okay, then what is the wavelength of the light? So again, it's the same. We can use the same formula as we used before, which is 2d naught equal to P lambda, and lambda is just 2d naught by P, which is 2 into 0.022 mm by 100. It's 44,000 angstrom. Okay. The same formula can be applied here also. So the main concept here to learn is, whatever you do, if you change the distance between the two interfering beams, the fringes will either appear or disappear. Okay, and the distance with which you change is given by D naught, and the fringes that will appear and disappear is given by P, and lambda is the wavelength of light. So you can use this formula to calculate the wavelength of the light during the experiment. So it's a very nice experiment. You can use any source of light and you can calculate its wavelength if it's monochromatic source. So you might perform this experiment in a lab if you have a Michelson interferometer. And okay, then The next problem we have, this one is also on Michelson interferometer. So here again, a plate of thickness 0.025 mm is placed in the path of Michelson interferometer. A shift of 50 fringes is observed for a light of wavelength 4000 angstrom. Now here we are asked what is the refractive index of the plate. So we can use the same formula that we used here, this formula, correct? But now we have everything instead of uh, here we are asked wavelength. Now we are asked to calculate the refractive index. Okay, so let me write the formula here. 2 minus 1 t equal to p lambda. So mu will be just e lambda by 2t plus 1, and everything is given. Sorry, p. P is 50, lambda is 4000 angstrom, uh, that is 10 to the power minus 10 meters, and 2 into T is 0.025 mm, that is minus 3 meters, and plus 1. So if you calculate everything, you will get 0. Sorry, not 1.4. So this is your this is the refractive index of the glass plate. Okay. So if you know the source of so you know the source that you are using for Michelson interferometer experiment, you can uh, calculate the refractive index of any material using Michelson interferometer. So this simple experiment it's very powerful. Okay. Any question? Have you ever done this experiment in a lab? It's a experiment for BSc Physics honors. Uh, it's a very interesting experiment to do. Okay, let me go to the next problem. Now this problem is based on Newton's ring. And the question is, in Newton's ring experiment, the diameter of 12th ring changes from 1.5 centimeter to 1.3 centimeter when a liquid is introduced between the lens and the glass plate. Okay, so you remember the Newton's rings experiment. You have a plano-convex lens, you have a glass plate like this. Now between this lens and this glass plate, a liquid is introduced. Okay, so this is now immersed in a liquid, the whole apparatus. and you have to calculate the refractive index of this liquid. And the, what is given is uh, the diameter of 12th ring. Okay, so D12, it changes from 1.5 centimeter to 1.3 centimeter. Okay, now you remember the formula for diameter, right? So here in the Newton's law. So this is the formula for diameter for so suppose if the refractive index of the medium is 1, this is the formula, and if the refractive index of medium is mu, this is the formula. Okay, and now we can use this formula. So let me write it. Yeah, so dm square is equal to 4m lambda r by mu. Okay, now for air, mu equal to 1, so d12 square will be just 4 into 12 into lambda into r divided by 1, and the so the r is for air, the r is given, it's 1.5 centimeter. So 1.5 minus 10 to power 2 minus 2, and then for liquid whose mu has not changed, okay, so mu greater than 1, we don't know what that is, its diameter will be given by 4 into 12 into lambda into 1.3 and divided by mu. That is refractive index of the liquid. Now we can divide these two equations. Okay. Oh, sorry. Uh, this r is not the radius of the ring, which is the radius of curvature. So, and we don't know, but it doesn't matter. It will get cancelled, and this is the d prime will be the radius diameter of the ring when we introduce the liquid. So if we divide these two equations, we'll get an expression. This d prime square, and so everything will get cancelled, correct? This thing will get cancelled, and you will get is equal to mu only. So mu is just, and d So diameter, when the, there is air between them, is 1.5 centimeter, and when the liquid introduced is 1.3 centimeter. Okay, so when you divide this, you will get 1.33. Okay. So this is the refractive index of the liquid. Option B. Correct. Any question here? You guys are not responding. Sankar, is it fine? Shahida, Talat. Okay, okay. Thank you. If you have any question, you can just ask. Okay. Yeah. Okay. Let's go to the ninth problem. This is also based on Newton's ring. So here, uh, in a Newton's ring experiment, the diameter of 12th ring, 20th ring, sorry, 20th ring was found to be 0.80 centimeter, and that of the 10th ring is found to be 0.60 centimeter. Okay, and if the radius of curvature of the lens is 120 centimeter, we have to find the wavelength of the light. Okay, so how do you solve this problem? You have diameter of two different rings given, and the radius of curvature is given, and you are asked to find the wavelength of the light. Okay, uh, so what do you do? So we can use the same formula that we used last time, which is dm square is equal to 4m lambda r. Okay, considering that the medium here is air. Okay, which is that means the refractive index is just 1. Now, and we have another diameter, so dm plus p is dm plus p lambda r, right? So what you can do is we can just subtract these. Okay, so dm plus p square minus dm square is equal to, so when you subtract these two equation, you will get 4p lambda r. Correct. Now what is p? P here is 10, right? Because the m is your suppose uh, 10th ring, and the other diameter is given of 23. So the difference between them is 10. So that's your T. Okay, so you can just put all the information that you have now. So DMP square is 0.8 square minus 0.6 square. These are in centimeters, so we have to multiply by 10 to the power minus 4 to get it in meters. Then you have 4 into 10. You need lambda, wavelength of light, and the radius is given as 120 centimeters. So again 10 to the power minus 2. Okay, so you can perform this calculation, and you will get the answer of lambda as, so lambda will be just 0.8 square minus, let's solve a little bit more. So 0.64 minus 0.36, right? And so 10 to the power minus 2 will remain by cancelling it from the other side, and in the denominator you have 40 into 120, correct? And then here you can have, so 64 minus 36 will give you 28, right? Into 10 to the power minus 4 divided by 4800, correct? Yeah, you can use calculator. Just 583 extra. Yeah, thank you, Talak. It's the correct answer. So this is another application of frequency in the experiment. You can calculate the wavelength of the light that you are using. You can just measure the two rings, and you know the radius of curvature of the plano-convex lens. Okay. Now the 10th problem. Here the Newton's rings are observed with the light of wavelength 5000 angstrom. Okay, so here wavelength is given, suppose, of the light that you are using, and the diameter of 20th dark ring is given, which is 0.40 centimeter, and you have to find the radius of curvature of the lens used. Same thing, same application. So suppose in an experiment you don't know the radius of curvature of the plano-convex lens that you're using, but you know the wavelength of the light, so then you can calculate the radius of curvature by the same formula. So you have this formula. So R will be just dm square by 4 lambda, and dm is 0.40 square 4, and the V that we are talking about is 20. So 20, this is 5,000. Okay, and you can do this calculation in your calculator, and this is in angstrom per minus 10. Wait. Yeah, yeah. So it will be 16 into 10 to the minus 2 divided by, so 5 to the 10, uh, 8 into 5 to 10 to the power 4 here, 10 to the power 6, right? 1600 5 centimeter, so it will be just 40 centimeter, correct? So the radius of the curvature is 40 centimeter. Yeah, thank you. Now the last problem of today's session. So here, in a Newton's ring experiment, the diameter of fourth ring is 0.25 centimeter. So diameter of fourth ring is given. Centimeter, and diameter of 14th ring is given 0.8 centimeter, and we have to find the diameter of 24th ring. Okay, now can anyone tell me how to solve this one? So again, I mean, the formula we have is the same. dm square is equal to 4 r, correct? So by taking ratio, are you sure? So you are saying that we can take, so suppose d4 square will be 4 into 4 lambda r, and we just divide it by d14 square, which will be 4 into 1 4 lambda r. So everything will cancel. 4 will cancel, so you will have a relation between d4 and d14 square. Right? Now what? So sorry, 4 by 14. Now what you will do? Talat, tell me what will you do next? So taking the ratio, yeah, okay, you try. So taking the ratio is not a correct way. Okay, I'll give you some time to try. You figure it out and tell me. Others can also try. So the way you can think here is that uh, this to calculate the D24 uh, you need, so what do you need? You need the, so m, you know it's 24. You need lambda and you need r. Okay, so since when you take the ratio, this get cancelled, you cannot get information of lambda and r. So one thing you can do is, so let's write two equation, 4 into 4 into lambda r, and then you have d14, which is 4 into 14 into lambda r. You can subtract these two, right? So d14 square minus d4 square is equal to 4, and 14 minus 4 is 10 into lambda r. So now you have lambda r, which is equal to, so the d14 is 0.8 square, d4 is 0.24 square, 25 square, and you divide by 40. So now you have the information of lambda r, you can just put here. So d24 square is just 4 into 24 into 0.8 square minus 0.5 square divided by 40. Correct? And if you calculate this, uh, d24 square, you will get 1.2175. So diameter will be just square root of this, which is 1.03 centimeter. Correct? So this we have to think uh, what information you need. to solve the problem. Accordingly, you imply the ratio of so this is the last problem for today. Do you have any question in any problems that I discussed? Or anything you want to ask? Okay. So thank you for joining. I'll see you next Saturday. I'll close the meeting.